Today we're going to look at 5 very specific properties of elements pertaining to their electron configuration. So as you can see here, the 5 properties we're going to look at are called atomic radii, ionization energy, electron affinity, ionic radii, and electronegativity. And we've got just a simple 2-letter symbol there, so you don't have to actually write out the entire name. So what we'll do in this video is identify each one of these properties, what they mean, also be able to make some predictions in terms of comparisons between elements. The very first one, atomic radii. Simple as it sounds, it's talking about the distance that an atom has for its radius. Now, what's kind of tough is it's difficult to identify in one atom exactly where what the radius is, because the electrons are in a cloud, hence the just pure chaos that exists in terms of where the electrons are going to be. We realize from chapter 4, atoms have orbitals. Electrons can be in the various orbitals, the various sublevels, the various levels, all over the place. So it's very difficult to measure that distance for one atom. But what we can do is measure the distance between 2 atoms. More specifically, the distance between 2 nuclei. Nuclei are very dense particles, and so through experimentation instruments, we can measure the distance between 2 nuclei. Therefore, the radius for one is half of that distance between the 2 nuclei. And again, we're talking on the ranges of several picometers to maybe 100 or 200 picometers. Okay, remember, milli is -3, micro is 10 to the -6, nano is 10 to the -9, pico is 10 to the -12 meters. Extremely small. Right? So, what do we need to know about atomic radii? Well, what we're going to do is we're going to look at a periodic table. So, if you have one out, that's good. If you don't, I would suggest you kind of get one out here as we talk. But what we're going to do is we're going to look at what we call trends. And the 2 trends that we're going to look at in all 5 of these properties are what we call group trends. So what happens is we go down the periodic table, and period trends. And more specifically, what happens is we go left to right across a period. So if we have a periodic table, when we say group trend, we're talking about, well, what happens as we go down a column in terms of the atom's radius. Okay? So we go down a particular group. What does that tell us? We're also going to look at going across rows or across periods. What do we know about the size of an atom as we go left to right across a particular row? Okay? So that's the purpose here of what we're trying to do. So, group trend. And again, these are things that you're going to have to know. You always have a periodic table, so to be able to make comparisons, you just need to know as you move through the table what it means. So, group trends. As you go down a group, basically we're adding more levels or layers to an atom. Well, if we're adding more levels or layers, it's just getting bigger, you know. And this is the old model of an atom that we know is really not correct. If something's got 3 levels in it, it's going to be a lot bigger than something that has 1, or a lot, or smaller than something that has 4. So the farther down on any periodic table, the more levels you have. That's simple. Period trend. As you go across a period, it is going to get smaller. The atoms are going to get smaller. So again, as we go left to right across the periodic table, they're getting smaller. Now, the reason for them getting smaller, well, first of all, we're not adding electrons in layers farther away. They're being added to the same level. So we're talking about electrons in level 3 as we go across a row, or level 4. But here's why it actually shrinks. We're adding electrons, but we're adding them to the same level or orbital. So they're not getting further away. Okay. But at the same time, we're adding more protons to the nucleus. Well, if we're adding more protons to the nucleus is gaining a much stronger positive charge. So if we have all these electrons that are being added as we go across a row, but they're not being added at a greater distance, and at the same time the nucleus keeps adding protons, and if the electrons aren't getting further away, what starts to happen is those electrons are getting pulled in, and we actually see the atoms shrink because, again, we're adding electrons, but we're not adding them at a greater distance. Right? So, if you look at a periodic table, clear this off. Okay? So we go down any column right here. Every atom is getting larger as we go down a column. As we go across a row, every atom is getting a little bit smaller. Now, I'm not getting into crazy little details, but if you look at page 151 in your book, it has the little green dots that basically give you a visual representation. Now, there are small little instances where we see the numbers maybe bounce up or bounce down, things like that. We're not going to talk right now about what those little variations are. This is more of a global trend. Just in general, left to right, what happens? In general, top down, what happens? So here's what I want you to do. I want you to pause this screen, and I've got two different questions here. I want you to rank these four atoms in terms of largest radius down to which one has the smallest radius. And then we'll come back and we'll talk about these. Again, you'll need a periodic table. Obviously, you'll need to look up at the trends and kind of use those together to figure out the answers. Okay, so the elements that I had you rank are right here. As you can see, the answers are potassium, sodium, sulfur, fluorine, rubidium, magnesium, and phosphorus. Now, real quickly, why is that the order? Well, if we go to our trends, let me pull up the periodic table here. If we go to our trends, we have sodium, we have potassium. And basically, I guess here's how I'd approach it. Just pick two at a time, and based upon the trend, decide which one's larger. Sodium and potassium are in the same group. Therefore, potassium is larger. Okay. Then we have sulfur and fluorine. Well, you might say, you know what? Sodium is in the same row as sulfur. Therefore, sodium is larger because it's farther to the left. So potassium, sodium, sulfur. Now the last one is fluorine compared to all three. Well, if we can see, fluorine is higher up than any element, and it's the farthest to the right. So not only has it had the least number of levels, it's the farthest to the right, which has the biggest proton to electron ratio. So fluorine would be the smallest atom out of all these. So in general, we've seen right now, where are the bigger atoms? Over here. Where are the smaller atoms? Over here. Okay, so we'll talk about that. If we come back to the other ones, rubidium, magnesium, and phosphorus. So, rubidium, magnesium, phosphorus. And you say, oh, magnesium and phosphorus are in the same row. Phosphorus is farther to the right. Therefore, it's smaller. So magnesium followed by phosphorus. And then we've got rubidium compared to magnesium. Well, rubidium is lower, and it's to the left. So it's lower, which means bigger, and it's to the left. So in both cases, it's larger. So lower, left, equals larger. Okay. And so that gives us a comparison. Now, speaking real quickly about diagonals. Some diagonals might be tough to predict, so I'll just give you a comparison here on what these are. Okay, so here's a comparison. Well, the magnesium rubidium, that's easy, because magnesium is higher up and it's to the right. So again, we made that comparison. Left and lower is larger, therefore up and to the right is smaller. Well, what if I have a comparison instead of magnesium and rubidium, what if I have a comparison of strontium and potassium? Well, here we've got a sort of a conflicting trends. Strontium is lower, therefore we would say larger, but potassium is to the left. So left is the potassium, lower is the strontium. That diagonal is impossible to predict just upon a description. So what does that mean? That means you're not going to see those diagonals. Yes, you could see diagonals this way. Okay? Potassium is lower and left, therefore larger, but you are not going to see diagonals the other way. Okay, so again, you'll never see a description where there's a contradiction. All right, the next one is ionization energy. It's the amount of energy needed to remove an electron from an atom. Now here's the thing when we talk about this. We're going to talk about any element that could possibly lose an electron, but we're going to find out in reality, some elements will lose, but there's other elements that really don't lose. But we're going to kind of, theoretically say, if they all lose, this is what happens. So, how much energy it is needed to completely remove an electron from an atom? First of all, if that happens, we no longer call it an atom, we call it an ion. So if element A loses an electron, it becomes an A with a plus charge. Now, what does that mean? Well, we say it in terms of electrons. That means we now have less electrons than we do protons. If we wanted to kind of write a little equation, we would say we have an atom, we add energy to it, that energy causes the electron to separate. Remember, this doesn't mean we made an electron. What this means is we separated the electron from the atom. And now this is called an ion. Okay. So we're going to kind of talk about how easy or how difficult is it to remove an electron from an atom. So the first thing we're going to talk about is the trends. So our period trend, left to right, you can see there, it gets higher. This is an important piece. That means it's going to get harder to remove an electron. Well, why is that? Well, let's go back to atomic radii. It's smaller. The smaller the atom is, the closer the electrons are to the nucleus. What's the second reason? Well, as we move farther to the right, okay, this is chapter 4, we're talking about electron configuration. So we're talking about P3, P4, P5, P6. We're moving closer to full. Now, if we're on the left-hand side, it's less energy. Well, if we're on the left-hand side, that means it's more empty. Okay? So there we've got a period trend. Our group trend, going down. What happens? Well, as we go down, it takes less energy to remove an electron. Therefore, that's easier to remove. Why is that? Number one reason, the atoms are larger. If the electrons are getting farther away from the nucleus, it's going to be easier to take them away completely. We can also talk about, are the orbitals full or empty, depending upon a specific situation. So, what I want you to do is look at these three, and I've written their electron configuration out just for convenience, but you really don't have to have it, because if you've got a periodic table, we can figure these out. So rank these in terms of ionization energy. Say that fast 3 times. From highest to lowest. So what that means is which one of those 3 elements is going to be the most difficult to remove an electron from, followed by the middle one, and then the last one written would be the easiest to lose an electron from. Okay, so pause this, work on that, and then we'll kind of keep moving. Okay, so here's the correct answers. Magnesium, followed by aluminum, followed by sodium. Now, some people might say, wait a second, shouldn't it be aluminum first? Well, remember, there's 2 pieces. Number 1 is we're talking about, okay, so back to our justification as to why it gets easier or more difficult to remove electrons. If we come back to a periodic table, we can see it from here. As we go down a group, the atoms are getting larger. So if it's getting larger, that means these electrons are getting further and further away from the nucleus. So it's going to be easier taking away an electron from francium than it will be rubidium. It'll be easier to take one away from sodium compared to rubidium. Now as we go across a row, the atoms are getting smaller, and we're getting closer to P6. So arsenic, it's going to be a little bit easier to take one away from arsenic than selenium. Arsenic's a little bit larger, and it's a P3 compared to a P4. Selenium is going to be a little bit easier to take one away from than bromine. Why? Selenium's a little larger, and it's a P4 compared to a P5, and so on. So we have those comparisons that we can make based upon their position on the periodic table. Now, what we'll do next here, and this is something you can kind of work on, is second ionization energy and third ionization energy. So now what we're talking about is, what if we take away one electron, then we try to take away a second or a third? So what I want you to do is think about, we already know what the order is to take away one electron from sodium, magnesium, and aluminum. What I want you to do now is, okay, go ahead and take that one electron away, and now revisit the electron configuration to see what element will now be the hardest to take away that second electron away from. And then finally, to take away the third from. So what I want you to do is finish this to show me in class, and actually we might take a little bit of time in class to talk about it also. Okay? Make sure you have a periodic table available so you can obviously reference that.